Welcome back to today's video. Today we're going to extend another concept from the one-dimensional analysis that we did in the first semester to higher dimensions, and that is continuity. So this is going to be chapter 12.4, continuity. So you remember we defined continuity in on the real line through limits of functions. The idea here was we defined the limit of a function first, and then we took the limit of that function towards a certain x value. And when that limit agreed with the actual function value, then we said that this function was continuous. So it kind of did what was expected from its behavior around a certain point. So the first thing we need to do is we need to extend the notion of function limits, and then we can define the notion of continuity in the same way as we did for one-dimensional functions. And that's going to be our first definition. So, as usual, let x be a subset of r to the n. Let f be a function on x to some r to the m. And we consider a point x star in x. Then let's first define a function limit. We will say that a in r to the m is called the limit of f for x tends to x star if the following holds. What we do is, as in one dimensions, we're taking a sequence that converges to x star, and then we use that to define a sequence of function values and see if that also converges to a. And we do this for every possible function that is in the domain x and converges to x star. If that works for every possible sequence with these properties, then we say that f of x converges to a. Okay, so for every sequence a k and 0 in x that converges to x star, the sequence of function values, so the sequence defined by f of a k in n 0, that also converges, and it converges to that limit a. Okay, the notation is the same as in one dimension, so we just denote this by limit of f of x as x tends to x star equals a. Second part of our definition, we can now extend the definition of continuity, and we can say f is called continuous in a point x star if the limit of f of x as x tends to x star is the same as the function value at x star. So nothing unexpected happens. And finally, part 3 of the definition, you know that one as well. F is called continuous on the domain X if it is continuous for every point in that domain. So F is called continuous in capital X if F is continuous in every point x star in X. Similar to one-dimensional theory, we again have a couple of properties for continuous functions. Specifically, we can most often argue that continuous functions are just composed of a bunch of simpler functions, and we know that these simpler functions are continuous, so the composition will also be continuous. Yeah, so things like the sum of continuous functions, the difference of continuous functions, the product of continuous functions if it is defined, also dividing continuous functions if the division is defined, things like those will all result in continuous functions again. So let's formulate that as a theorem. We consider again a domain X, so let X be a subset of Rn. And we consider functions f, g defined on X to Rm. And also we consider a function g tilde defined on X with values just in R. And let those functions be continuous on X. And let alpha be a real number, just a constant. Then the following is true. First, the sum of two continuous functions is again continuous. The multiplication of a continuous function by some constant, alpha, is continuous, so alpha f is continuous. And also the multiplication of two continuous functions, if it is defined, is continuous. And we just have a look at the continuous functions g tilde and f. So we multiply the vector valued function f with the real valued function g that is obviously defined. All of those are continuous. On X. Second, we can also divide functions, and of course we did not define a vector division. That cannot be defined usually, but we can divide a function by a real value function. So a function like f divided by g tilde is continuous on the domain X, with the exception of X values where g tilde assumes a value of 0. So we need to take out all X in X where g tilde of X is 0. And same thing for the division by a constant, f over alpha is continuous, of course, for alpha not equal to 0. Next thing we can do is we can compose two functions. So let's define another function here in another domain. Let y be in some r to the k, and consider a function h defined on y with codomain in x. Let's say this is continuous. Then we can look at the composition of f and y. So first f and h, sorry. So first h, then f, or f after h. This function is again continuous. And finally, again, a simple correspondence to the one-dimensional case. We've seen that in sequence convergence already. Of course, it also carries over to function convergence and then to continuity. So if we have a vector-valued function and then look at the coordinate functions, then we can say that f is continuous if and only if all of these coordinate functions are continuous. So if f of x is of the form f1 of x to fm of x, then f is continuous on x if and only if f1 and f2 and f3 and so on up to fm that are functions that map the domain x to R if and only if all of these are continuous on x. Okay, so the definition is pretty straightforward. If we have a vector-valued function, the idea is we need only take a look at all the coordinates, see if those are continuous, and basically the idea is, again, we just use simple functions that we know and then compose them, add them, divide them, multiply them to get the function that we actually want. And we argue that those simple functions are continuous, so the composed function will also be continuous. Let's have a look at a quick example. So, first example is this one. Let's consider the function f of x1 and x2. So, from R2, defined by, we'll have two coordinates. The first one is going to be x1 cosine of x2. And the second is going to be e to the x1 plus x2 minus 1. So this is a function from R2 to R2. And I claim that this function is continuous. And this is for the following reasons. First, we can look at the two components in turn. So f is continuous if and only if both coordinate functions are continuous. And those coordinate functions are f1 of x1, x2 equals x1 times cosine of x2. And the other one is f2 of x1, x2 equals e to the x1 plus x2 minus 1. Okay, second argument for f1. Obviously, this is a product of two one-dimensional continuous functions, and thus continuous. F1 is a product of continuous functions, and thus continuous itself. And for F2, a similar argument holds, that is sum of two functions, and the first of these is an exponential function, which is a composition of a simple one-dimensional exponential function and a sum of two values, and the sum is obviously continuous as well. Okay, so F2 is the sum of two functions The first of these is x1, x2 maps to e to the x1 plus x2. And this is continuous as it is a composition of two continuous functions. And altogether this means F2 is continuous. Okay, so that's the typical argument. Same thing as with the real numbers. Functions are usually continuous because they are composed of continuous functions. Okay, let's have another look at a class of functions that will be of importance later on. We first define what those functions look like. Definition. We're going to define so-called multivariate polynomials. A multivariate polynomial is a function that is similar to a polynomial, but instead of just one variable x, it has several variables that may be combined. So this is a function p from r to the n to r of the following form. So p of x, or rather p of x1 to xn, is a sum of terms of the following form. We have a constant, let's call that gamma I. I'm going to define that I in just a minute. And then of just an x to some coefficient. What we have here is x1 to some I1 times x2 to some I2 and so on up to xn to some in. So all the possible x variables show up. Each of those is taken to a certain power and they are multiplied. And then all of these expressions are summed up. So pretty similar to a one-dimensional polynomial. And we're going to sum over I in a certain index set, capital I, where this capital I is a subset of the set 1 to k to the n for some power k. So basically we are assigning each of those x1, x2, x3 some power between 1 and k. And actually we also want to allow 0 here. So not necessarily every variable needs to be present in every of these multivariate monomials. Okay, and this is true for some finite k in n. And the gamma i's, those are just real constants. Okay, let's have an example of those. Example. For example, a typical multivariate polynomial could look like this. P of x1, x2, x3. Let's have a three-dimensional, three-variate polynomial. Let's say first we have something like 2x1 to the 2x2. Then we have a term like 4x1 times x2 times x3 to the 3. And finally, let's say we have minus 8 x2 to the 3 x3 to the 3. So that's what a multivariate polynomial could look like. Yeah, for example, what we have here, this is our gamma 1 or gamma I1. Yeah. The I in this case is 2, 1, 0. x1 is taken to the power of 2, x2 is taken to a power of 1, and x3 is taken to a power of 0. Yeah, so this corresponds to x1 to the 2, x2 to the 1, x3 to the 0. Okay, same thing here. This is again the gamma. The I in this case is 1, 1, 3. And for the last one, the minus 8 here, that is gamma. And the I in this case is 0, 3, 3. Okay, so that's how this general definition can be applied. Okay, and what we can say is that multivariate polynomials are continuous functions on Rn. That's why we're talking about those in this chapter. Multivariate polynomials are continuous on R to the n. And the reasoning is similar to the one that we've just seen. First reason is a multivariate polynomial is a sum of simpler functions, the so-called multivariate monomials. Okay? Sum of simpler functions of the form gamma I, x1 to the I1 times and so on, xn to the In. Those are called multivariate monomials. And each such monomial is, again, a product of a constant and univariate monomials, very simple functions that we know already. Okay, so each of those is a product of a constant and univariate monomials. And we already know these are continuous. Okay, so the multivariate polynomials are also continuous. Okay, we'll conclude this chapter with another theorem that will be important at a later point, and that somehow relates the notion of continuity to the topological notions that we've discussed before. So let me state that theorem now. Again, we'll consider a function f on some domain x. So let x be a subset of R to the n. Let f be a function from x to R to the m. And then f is continuous if one of the following characterizations hold. And let me write that down first. Then f is continuous if and only if two characterizations. The first one, for any open set in the codomain, the pre-image of that set is again open. So in other words, open sets generated by a continuous function always come from open sets. So for any open set y in R to the m, the pre-image, and the pre-image is denoted by f to the minus 1 of I, and that just consists of all x in the domain that map onto some point in y. So f of x is in y. All the points that map to y. This is also open. Okay, and the second characterization is for every closed set, the pre-image is also closed. So that also holds for closed sets. Every closed set y subset of R to the m, the pre-image f to the minus 1 of y is also closed. Okay, and actually this theorem can even be used to characterize continuous functions without resorting to sequences. So pretty much everything that you need to know about continuity can be captured by this characterization. You can just say a function is continuous if this property holds, that the pre-image of every open set is again open. So you can define continuity on spaces where you only have a notion of openness. You don't even need to be able to define convergence properly. You don't need to be able to measure distances. That's all you need is a notion of what an open set means. And then you can define continuous functions. Yeah, and this is done in functional analysis, but this is going too far for this course, so we won't deal with this. But the theorem will be of some use later on. And finally, a theorem that is of more or less immediate use. Something that we usually want to do with functions is we want to optimize over them. We want to find their minima and their maxima. And of course, to do that, we need to be sure that these minima and maxima actually exist. You will remember that over the reals, we had something like a function, a continuous function assumes its minima and maxima over a closed interval. And something similar holds in the multidimensional case as well. It turns out closed is not enough in this case, obviously, because the set may still not be bounded, and we wouldn't expect a function to attain its maxima or minima over an unbounded set. So what we need to have actually is closedness and boundedness, so compactness of the domain. And then we can show that a function attains minima and maxima over that domain. And that's going to be the last theorem for this video. So let x be in R to the n, f from x to R, and we can formulate this as R to the m even. And let this be continuous. Then the first thing that we can say is if x is compact, then the image is also compact. And that holds even if the codomain is in R to the m. If x is compact, then f of x is also compact. And remember, compact, that means closed and bounded. Okay, and in particular, this implies what we wanted. This implies if we have a compact domain for compact x in R to the n with x not the empty set, we should exclude that case because that's not very interesting. And a continuous function f from x to r, and now we're only going to r because we want to minimize or maximize, and of course a minimum and maximum is only defined over the real numbers. We cannot properly define that over r to the m. Okay, so a function like this attains its minimum and maximum over the domain x. The function f attains its minimum and maximum over x. So it makes actually sense to minimize such a function if we have a compact domain, and that will usually be the case for the examples that we will be looking at. Okay, this includes this introduction into continuity. Next, we'll have a brief glimpse of how continuity in more than one dimension may actually be different from one-dimensional continuity, to get an idea of how this will then later translate to differentiability. I'll see you in the next video then.